This is Paul, the SDR guy. And what we're going to do in today's video is I'm going to go through a presentation that I made to our local amateur radio club. This is the Smoky Mountain Amateur Radio Club, or SMARC. Now, if you're watching this video and saying, I'm not an amateur radio guy, so I'm going to pass. Well, if you would do that, that would be the wrong decision. The reason being is this presentation is entitled Introduction to SDRs and GNU Radio. And there will be some interesting things in here for you. And with that, let's get going. I'd like to begin by giving you a brief my journey. Well, in 2019, I was visiting a good friend of mine, Marty Porter. His call sign is N5SXV, and he had just received a package from Amazon. He opened it up. I looked at it and I said, "What is this?" And he said, "Well, this is an SDR." And I said, "Well, what in the world is an SDR?" And hence my journey with SDRs began. And Marty also said, and by the way, I'm a licensed amateur radio operator. And I said, "Well, tell me more." One thing led to another, and I became a licensed amateur in 2020. And Marty introduced me to a friend of his, Rick Tromer. His call is W5NR, and Rick was and is my Elmer. And Rick has helped me along the way so much, I can't even begin to thank him. And what this is about, it's all about hams helping hams. I have been a member of the Smoky Mountain Amateur Radio Club. The acronym is SMARC, for about 2 years. Many members of SMARC have helped me. Most recently, a ham friend is building me a 10 gigahertz system with the assistance from another ham machinist. They are also building the hardware for a home brew HF transceiver. I'm creating the software. We will have a future video or series of videos that will cover this entire project. Okay, let's go ahead and get going with the presentation. Introduction to Software-Defined Radios and GNU Radio. This is Paul, the SDR guy, of course. My amateur radio call sign is KI5MIV. And I received a great deal of assistance from Gary Schaefer, Don Mills, and Jeffrey Mark. Thank you all so much. This presentation was given to the Smoky Mountain Amateur Radio Club on 8/25 of 2025, and this is a technical presentation. During the presentation, we raffled off an SDR, so sorry YouTubers, you missed out on this. Well, what is an SDR? A software-defined radio is a radio communication system where traditional hardware components like mixers, filters, amplifiers, modulators, demodulators, and detectors are replaced or implemented by software running on a computer or an embedded system. We often see in higher-end SDRs that FPGAs are used. Let's look at a simplified version of how an SDR works. But first, let's note that in a conventional radio, each function, tuning, filtering, modulation, so on and so forth, is handled by dedicated electronic circuits. In an SDR, the radio frequency signals are converted into digital signals using an analog to digital converter. Once in digital form, most of the signal processing is done in software. A digital to analog converter can be used to transmit signals back out if you have an SDR that has transmit capabilities. Well, what are the advantages of an SDR? Well, first up would be flexibility. A single SDR can handle many communication standards. For example, FM, AM, single sideband, Wi-Fi, LTE, and many, many more simply by changing software. It also shines in the area of upgradability. Features and protocols can be updated without changing the hardware. SDRs have a wideband capability. SDRs can tune across a broad frequency spectrum. SDRs are very popular with hobbyists, researchers, and military, since new modulation techniques can be tested without building new hardware. Let's meet the ubiquitous RTL-SDR. And what can we use one of these for? Well, for amateur radio, for starters, we can listen to VHF and HF amateur radio. We can use them to decode APRS packets. We can listen to amateur radio hams on single sideband using lower sideband and upper sideband modulation. We can listen to satellites and the International Space Station. We can decode unencrypted digital voice transmissions such as P25, DMR, and D-Star. We can use an RTL-SDR as a PAN adapter for your traditional hardware radio. And for those of you that don't know, a PAN adapter, essentially you'd have another screen and usually a computer that you would plug your RTL-SDR into, and it lets you look at additional section of bandwidth while you're using your radio. And we can also use this thing as a spectrum analyzer. I jokingly call this a poor man or an affordable spectrum analyzer. And this list just scratches the tip of an iceberg. There are many, many more applications for, that are related to amateur radio, but so much more. Well, the RTL-SDR, this actually started out as a TV tuner, but along the way, some smart people came up with an alternative use and realized that this could be used as part of an SDR. Well, the major components of this are an RF front end. This is the tuner section, followed by a digitizer. This uses an analog to digital converter. The output of this goes to a Quadrature demodulator. General SDR signal flows for the RTL-SDR signal hound. You start with a tuner, then a digitizer, and then a Quadrature demodulator that outputs I and Q. Below that, we see for the HAC RF1, USRP, and Lime SDRs, we have a tuner followed by a Quadrature demodulator and then I and Q. Well, You're probably asking yourself, what's IQ and what's a quadrature demodulator? Well, hold those questions. We will revisit IQ after we introduce GNU Radio. Well, what in the world is GNU Radio? Well, GNU Radio is an open source software development toolkit used to build and simulate software-defined radios. It provides signal processing blocks that can be connected together to process real-world signals such as radio, television, satellite, or cellular communications entirely in software. What are some of the key features of GNU Radio? Well, it's based on using signal processing blocks. And GNU Radio comes with a whole library of ready-to-use filters, modulators, demodulators, FFTs, and more. GNU Radio uses a flow graph model. You don't need to know how to program software. Users can build what they call flow graphs, which are diagrams of how signals are processed from input to output. GNU Radio works with many SDR hardware platforms. For example, USRP, RTL-SDR, HackRF, and more, but we can also run GNU Radio in simulation mode without any hardware. The other very nice thing about GNU Radio is multi-platform. It runs on Linux, Mac OS, and Windows. Let's now switch to GNU Radio and let's build a simple FM receiver. We are now going to learn by doing. I don't know about you, but for me, I learn so much better if I actually do it when someone's explaining something to me. So let's go ahead and launch our GNU Radio. We're going to click on create a new flow graph. And by the way, if you don't know how to install GNU Radio, please see the playlist that I have that's regarding SDR basics. So what we're building is we're building a simple FM receiver. So we're going to come over here, click on the magnifying glass, and we're going to search for RTL-SDR, and we are going to use the one under Osmo SDR. We're going to left click with our mouse. We're going to bring it over here to the left side of our canvas and release the mouse, leave it there. And since this is a radio, we're going to be wanting to listen to audio. So we're going to search for audio, and we want to use an audio sync. And whenever you see red, that means that there's some kind of issue. Usually it's you don't have values populated or your block is not connected to anything. So the audio sync turns out to be, that's going to be your PC sound card. So let's double click on that. And what we're going to do is change the sample rate to 48 kilohertz. And that's all we need to do there. We are going to next click apply and then OK. Notice the sample rate now shows 48 kilohertz. We're going to come up here to this variable block for sample rate, and we're going to change it from 32,000 to 2.048 E6, and that's 2.048 megahertz. We're going to click apply. We're going to click OK. And the next thing we're going to do is I did a Google search on local FM radio stations. So I'm going to double click on the RTL-SDR source and the channel frequency. I'm going to make it 107.7 E6 because it's megahertz, and we will click apply and OK. Well, since we're listening to FM, we need to have some way to demodulate that. And broadcast FM is wideband. So we're going to type here WBFM. And how about that? There's a wideband FM receive block. And here you have it. And the next thing that we're going to need to use is called a rational resampler. Holy cow, what is that? Well, what this is going to be used to is to notice that we've got an input sample rate of 2,048,000 megahertz, and somehow we've got to reduce that frequency to 48 kilohertz. And so we're going to be using something that's known as interpolation and decimation to accomplish this for us. So to connect these blocks together, we're going to take the output of the RTL-SDR, we're going to hold down our left mouse button, keep it down, drag it over to the input of here, and release the mouse. Similarly, the output from here to here. And the thing I want to tell you is you have to make sure that the colors match. Here's blue. Blue stands for complex numbers. And then over here is orange. And orange is float. So we're going to connect this. What we're going to do next is double click on wideband FM receive, double click, and our quadrature rate is going to be 48,000 times, and we're going to use the asterisk for that, times 4. And then the audio decimation is going to be 4. We're going to click apply and OK, and we're not quite done. This rational resampler, we're going to put an interpolation of 3 and a decimation of 32, and we're going to click apply OK. So believe it or not, we have just created a FM receiver. And I'm going to run the flow graph here in just a moment, but I want to tell you that this is a commercial FM broadcast station. So due to copyright issues, I'm going to be turning the volume off very quickly. We have to give it a name. We'll call it First FM Receiver. And we're going to come to the lower right-hand corner. We're going to click Save. And you want to make sure that your RTL-SDR is plugged in before you start it, and that you have an antenna connected to you. There you go. So as you can see, this is incredibly simple and quick. It took me much longer to describe it than it would for you to actually do this without talking and explaining what's going on. So this is what I covered in the actual presentation, but what we're going to do is, since we're in a YouTube video, we have some more time. So we're going to make things a bit fancier, and we're going to do that by creating a user interface. And so when you think of a radio, what do you want to be able to do? Well, you want to be able to change channels, right? And so to do that in GNU Radio, we're going to come over here and we're going to search for Qt space GUI. GUI stands for Graphical User Interface. And what we're going to want to look for here is a range control. And so we're going to want one of these for frequency. We're going to also want one for gain. And we're also going to want to add ourselves a volume control. And so we're going to drag one more of these out here. And so we're going to begin with frequency. And we're going to change the label to frequency, and, the ID to frequency lowercase, the label to frequency. We're going to give it a default value of 107.7 megahertz, and we're going to start at 87.7 E6. We're going to stop at 107.9 E6. And we're going to do steps in 200 kilohertz. And once we have that input, then we're going to click apply and then OK. And for this particular control, we're going to delete the default value for ID. And we're going to call this RF gain. And here in the label, we will call it RF gain. And this is in dB. And in this particular case, we're going to make our default value 10. And we're going to start at 0. We're going to go to 50. And we'll keep the step at 1. And we're going to click apply. We're going to click OK. And next, we're going to go to this last one, which we're going to call volume. And for the volume, we're going to have a default value of -6. And we're going to start at -100. And we're going to stop at 10. And we're going to do steps of 0.1. And that is that. Well, there's another block that we're going to need to insert in here to act as a volume control. And that block is called multiply by a constant. So we're going to pick that. We're going to drag that over here into our flow graph. And we want to connect the output of wideband FM receive to the multiply by constant block. Well, look, the colors mismatch. So we need to change the multiply constant from complex to float. And we'll say apply, OK. Now the colors match. And what we're going to do is we're going to get rid of the arrow that's between wideband FM receive and the audio sync. We're going to do that by clicking on it and then hitting the delete key. And what we're going to do now is we're going to take the output of WBFM, connect it to the input and multiply by a constant, and the output of the multiply by constant back into the audio sync. Now notice we have a GUI volume control, and in order to use it here, we're going to double click on this again, and where it has constant, we're going to plug in volume here. And we're going to click apply and then OK. What we're going to do next is we're going to open up our RTL-SDR, and where it says frequency, where we hard-coded it to begin with, we're going to come up here and get the ID for the frequency. And we're going to plug that in there. We're going to scroll down to where it says RF gain, and we're going to plug in the ID from the GUI range control here, which is RF gain. We're going to next click apply, OK, and let's rerun our flow graph. So we're going to come back up here and click this button here. I apologize. The other one was still running. I'm going to turn that one off. That was our initial flow graph, and I'm going to execute this flow graph again. So notice now we have a nice little GUI interface here that allows us to change the volume, the RF gain, and the frequency. But let's not stop here. Let's take a look at some other ways that we can instrument this thing. Notice it says not titled. So let's close that dialog box. Let's come over here to options, and for title, let's call it First FM Receiver. Let's click apply. Let's say OK. Now, let's say we wanted to look at some scopes, if you will, something that would be like an oscilloscope, or something that would be like a spectrum analyzer. Once again, we're going to type in Qt GUI, and we're going to come down here to instrumentation underneath Qt, and we see a time sync here. And so let's drag that out here. And we also want to use a frequency sync. So we're going to grab one of those and drag it over here. And what we're going to do is connect both of these to the output of our RTL-SDR. And let's go ahead and run this flow graph again. And so here's the user interface. This particular signal would be what you would see if you were to connect an oscilloscope to the output here, and the bottom one would be what you would see on a spectrum analyzer. So how about all that? And we did this really very quickly. Again, it's taking longer because I'm explaining things to you. So let's go ahead and close this down. There's one other block that I want to mention to you. So if you have hardware, physical hardware connected to your flow graph, in this case, we have two things. We have our RTL-SDR that's plugged in, and the audio sync is our sound card. Well, many times as you use GNU Radio, you may want to do some things where you're not connected to actual hardware. And so in order to keep the flow graph from consuming all of the CPU, we're going to use this thing that's called a throttle. And you simply put this inline in your flow graph, and this will make sure, if you're, again, if you're not using any hardware, that you don't consume too much CPU. So this concludes our simple FM receiver build using GNU Radio. Some of you may have watched a TV show when you were younger called Lost in Space. And on this TV show, they had this robot that would wave its arms and say, "Danger, danger, Will Robertson." Well, the next few slides might cause your head to explode. We're going to need to understand a little bit of mathematics to understand what's going on here. And there's two different ways that you can approach this subject as a beginner. One is you can not be so concerned with what's an imaginary number and some of the things that's coming up next, and just jump to the conclusion that this is what's output from the RTL-SDR dongle and continue from there. But to achieve a little deeper understanding, we need to understand what an imaginary number is. Well, an imaginary number is the square root of -1. And if you recall from math, if you take a negative number times a negative number, that makes a positive number. Well, why do these things matter? Well, imaginary and complex numbers are not just made up, they're used in real-world applications. In this case, we're using them for signal processing, and they're used quite often in electrical engineering. The mathematicians use the lowercase I to indicate this, and in electrical engineering, they use J. Well, what's the relationship to complex numbers? Well, imaginary numbers are part of a complex number, which have the form a plus bi, where a is the real part and bi is the imaginary part. For example, 5 plus 3i is a complex number. Well, what does this look like on a complex plane? And for those of you that recall the XY Cartesian coordinate system, the up-down axis is called Y in that scenario, but here this is the complex plane. And we can actually graph numbers if we choose to do so. For example, if we go 1, 2, 3 to the right, that becomes the 3 that you see here. And if we go up 1, up 2, then that is 2i. And that brings us to this thing that's called a quadrature demodulator. And this can be a little bit confusing. This particular circuit that we see here does not demodulate things in, for example, FM or AM. What it does, however, is it takes an input signal and it uses a combination of a sine wave, a cosine wave, and a sine wave. And the cosine and sine waves have a 90-degree phase shift. Now the circles with the X in it, these are symbols for a mixer. So the RF signal comes in, goes into the mixer with a cosine. It then goes through a low-pass filter. Why it's doing that is beyond the scope of our session today, but this output is the I, or the in-phase component or channel. And down here, we're inputting a sine wave along with the input signal into a mixer, going through, once again, a low-pass filter, and out comes a quadrature signal or channel. There are some other names that are used for quadrature demodulator. One of them is quadrature mixer, and there's actually a number of other names, but those are two that are used. So we're going to be showing examples today using the RTL-SDR. And if you look very closely at the circle, there's a blue color coming out of it. That means that the RTL-SDR is outputting complex numbers. And those numbers are IQ, IQ, IQ. And one I and one Q together is a complex number. And these are, of course, fed into your computer through the USB. Next thing we're going to do is we're going to talk about sampling. There's a theorem that's called the Nyquist theorem, which says to accurately reconstruct a continuous signal from its samples, the sampling rate must be at least twice the highest frequency present in the signal. Human hearing ranges up to about 20 kilohertz. Well, maybe that's true for a newborn baby. To record audio without losing information, the sampling rate must be at least twice that, which is 40 kilohertz. That's why CD audio uses 44.1 kilohertz sampling rate. If we were to look at a picture of discrete samples that are created during this sampling process, we must first look at a continuous sine wave, and that's what we see here in the red. And the samples are simply taking a snapshot, and that's the value that's represented by these black circles at these particular moments in time. We're going to next talk about aliasing. So aliasing is a phenomenon that occurs when a continuous signal is sampled at a rate that is too low to capture its changes accurately. As a result, different signals become indistinguishable or appear as aliases of each other after sampling. Imagine you take snapshots of a moving object too slowly. It looks like it's moving differently than it actually is. Remember that similarly, if you sample a signal too slowly, high frequency components fold back and look like lower frequency components. Here's an example. If a 9 Hertz signal is sampled at 10 Hertz, the Nyquist frequency is half the sampling frequency. That's 5 Hertz. The 9 Hertz component will alias and appear as 1 Hertz. So instead of recording 9 Hertz, we see a fake 1 Hertz signal. So the moral of the story is we have to be careful with regard to preventing aliasing. Well, how do we prevent aliasing? Well, we just make sure we sample fast enough. And we do that by making sure that f of s, that's the sampling frequency, is greater than or equal to 2 times the maximum frequency. We also use an anti-aliasing filter. A low-pass filter before sampling removes frequencies above the sampling frequency divided by 2 so that no high frequencies fold back. How many of you remember the TV show, The Beverly Hillbillies? Well, if you remember this, you may not have noticed, but when they were driving down the road, they had spoked wheels. And as you were watching the car moving forward, it appeared that the wheels were rotating backwards. And this is an example of what happens with aliasing. And so, we want to think of a spinning wheel in a movie. And the movie is created by taking snapshots periodically. And if the frame rate, that's the sampling rate, is too low, the wheel may look like it's spinning slower backwards or standing still. And that is aliasing. The next thing that we're going to learn about is interpolation and decimation. Digital systems must operate on whole samples. You can't have partial samples. The SDR sample rate must be some specific value, but oftentimes outputs must be a different value. And when we have too many samples, it means too many computations and too much storage. Well, how do we answer that? We use interpolation, and that just means we increase the sample rate, and we use decimation to decrease the sample rate. And we do this by using integer values. So if we look at the picture that's down at the bottom here, we have a low-pass filter with a decimation of 10. And if we come over here to the rational resampler, we see an interpolation of 441 and a decimation of 2K. Interpolation is the process of increasing the number of samples between two known data points. Interpolation in digital signal processing increases the number of samples between discrete time samples through the process of upsampling and low-pass filtering. Interpolation increases the sampling rate for a signal such that a signal will appear to be sampled at a higher frequency. Figure 1 shows a sine wave with two sampling rates. And so we see the continuous signal here in orange, and we see green. And if we want to use interpolation by 5, and we would increase the number of samples from 15 samples in a low sampling rate sine wave to 125 samples in a high sampling rate sine wave. Interpolation, however, is a two-step process. It's always upsampling followed by a low-pass filter. If we upsample and do not use a low-pass filter, we have something similar to what is graphed here in the green. And this would, if this was audio, it would sound awful. However, if we use interpolation and low-pass filters, so you can see the combined effect here in green of both, then this maps to the higher frequency of the continuous time signal that we're hoping to replicate. And to make this green signal look just like this, we simply need to multiply by a constant. And after we do all of that, the thing this picture is showing us is the orange is the desired sampling rate, the desired higher sampling rate. And that by using interpolation with a low-pass filter, which is depicted with the green that you see here, then it maps very, very nicely. And this is in fact what is done, and it works very, very nicely. Well, we've talked about interpolation. Let's talk about decimation. So decimation means decrease sampling rate by dropping samples. So if we have a decimation rate of 3, then when you come across the very first sample, then you throw the next 2 away, keep the next one, throw the next 2 away, so on and so forth. And then this is the resulting sample rate that you would see after decimation. Well, we've learned about complex numbers, and we want to think about complex samples. So here's an example here. We have a I, or real component for this point, and we have a Q component. So this is I plus JQ. Once again, we're using a J because that's what electrical engineering and in signal processing use. Well, we can also find out the magnitude. So this is the point, and from the origin. This distance here is the magnitude, and I don't have a way mathematically to show the square root of this, but if we raise this I squared plus jq squared to the 1/2 power, that's the same thing as the square root. And the other major thing that we can get from these complex samples, is we can get the phase. And we can get that by taking the arctangent of q divided by I. Well, why does all of this matter? Well, it allows us to very easily demodulate signals. So for amplitude modulation, to get the magnitude, we take the square root of I squared plus jq squared. For phase modulation, we take the arctangent of q over I. And for FM demodulation, then we take, what this means is take the current sample, which is in, and subtract the phase of the prior sample, which is n minus 1. So here's a fun fact for you. Many of you may have an ICOM 7300 radio, and the sampling rate on this is 124.032 megahertz, and it digitizes the entire HF spectrum after filtering out some unwanted frequencies to prevent overloading. And we're talking about clipping of the analog to digital converter. It is then down converted in the digital domain. And by the way, this is done in an FPGA. These things are very, very fast. And it's demodulated. There is aliasing at some VHF frequencies, but that is outside of the ham bands. The next thing that we're going to do is we're going to switch to GNU Radio and look at narrowband FM and single sideband receivers.
And found out that we had an X flare that was in progress. One of the big flares, it was an X 8.6 or something like that. But
the last thing that we want to look at today is we want to look at an actual HF single sideband receiver. And this is the flow graph. Notice it's pretty darn complex. Lots of things are going on here. I'm primarily going to just show you the user interface here because I do not have an HF antenna connected at the moment. You can take a look at my video E18 and you can see this in operation. And I also give an explanation of how everything works. So let's go ahead and run the flow graph. And here we go. So in terms of the user interface, notice we can select the various ham bands from 80 meter up through 10 meter. You just click on the radio button for whatever you would like. You can choose upper or lower sideband by clicking on the drop down. The RF gain and IF gain of the RTL-SDR are controlled by these two sliders, and the volume is controlled here. If if you look in the lower left-hand corner of the full spectrum, notice the red. This red area is zoomed in to that portion of the spectrum, and as you would expect, you're zoomed into it right in this zoom spectrum area. Also take a look at audio level. When you're adjusting the volume, you're going to want to make sure that you don't clip. In other words, you don't go above -1 or below -1 or above +1. Let's next take a look at the Gain Adjust tab. This is an important one because it gives you a visual cue on your RF gain settings. And notice it's both RF and IF gain settings. And notice that there are two sliders here. And once again, as you're adjusting the gain, you don't want to clip. That means no greater than +1 or no greater than -1. The last tab we want to look at is the zoom waterfall. Again, we have no antenna connected, so we're not seeing any traffic here. But this user interface works pretty darn good. So this concludes our last example of the presentation. This is Paul, the SDR guy. Thank you for watching. Please consider liking the video and subscribing to the channel. Have a great day.